In this example, we have ourselves a nice radical equation, and it seems like we have a cube root of x minus 3 equaling x minus 9. If you'd like to try this problem first on your own, go ahead and do so, and come on back and we'll work a solution together. Okay, so looking at this, typically we solve radical equations by isolating the radical and then doing the inverse so we could cube both sides. But I'm going to try to avoid cubing the binomial x minus 9 because that's going to give us some pretty big numbers. So instead, let's consider using a u-substitution. So we'll say u equals, and it's going to equal this cube root expression, x minus 3. Okay, so the only other thing we need to do here, we have an equation here, u equals something in terms of x. So let's solve this equation for x and write it in terms of u. So we'll start by cubing both sides, because cubing u is much nicer than cubing x minus 9. So that equals x minus 3, and we can add 3 to both sides, and we'll see that u cubed plus 3 equals x. Okay, so this is good stuff. So we see that the left side of this equation is just going to be u, and the right side, x minus 9. Okay, well, x was u cubed plus 3, so it looks like it'll be u cubed plus 3 minus 9, so 3 minus 9 is minus 6. Okay, so this doesn't look too bad at all then. So our highest degree term is u cubed, and he's positive on the right side. So let's go ahead and subtract u from both sides, and we have 0 equals u cubed minus u minus 6. Okay, a much nicer equation than what we would have had if we had cubed the x minus 9. So let's go ahead and consider this now. Well, it's a cubic, and we're not going to be able to factor it outright. So let's consider the rational root theorem. So we have 6 here and a 1 here. So the possible rational roots will be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Let's see, a 1 and a negative 1, those won't work outright. So let's go on to 2. So 2 cubed minus, yeah, it looks like that guy will work. So let's go ahead and use synthetic division and take this 2 out. So the coefficients here are 1, 0, negative 1, and negative 6. Can't forget to put the 0 for the quadratic term since there, isn't one. And we'll use the synthetic division algorithm. We'll bring down the 1, we'll multiply, add, multiply, and add, multiply and add, and yeah, our remainder is 0. That's really nice. So it looks like right here we have 0 equals, and the factor we just took out was u minus 2, and the factor that's left is u squared plus 2u plus 3. All right, so let's consider now this quadratic. And let's take a look at its discriminant, b squared minus 4ac, because that'll tell us how many and what types of roots that we're going to have. So b squared will be 4 minus 4 times 1 times 3. That's negative 8. So that means we're going to have complex roots here, which is not actually going to give us anything useful. So the only value we care about is this u minus 2 equaling 0. So let's add 2 to both sides. We'll see that 2 equals u, or in fact, u equals 2. But this u value, of course, is going to be, well, in terms of u and not in x. So let's go ahead and plug it back up right here. So x will equal 2 cubed, which is 8, plus 3, which is 11. So x equals 11 is going to be a possible solution for us. But to ensure that it works and it's not going to be extraneous, let's go ahead and plug it back into this original equation. So we have the cube root of x minus 3 equals x minus 9. All right, so plugging in 11 right here, 11 minus 3 is 8, and the cube root of 8 is 2. And 11 minus 9 is 2 also. Yeah, so that works out. So our solution here for x equals 11 is going to be correct, and it's the only solution we have. And it worked when we plugged it back in. So here is our radical equation. We used a u-substitution to avoid cubing this x minus 9 binomial. And when we did so, we solved this polynomial equation. We put our u value back in terms of x, and here we go. X equals 11.